Hi class, welcome back to multivariable calculus. And today we're going to be starting our unit on integrating in multivariable calculus. So we're going to be using double and triple integrals. So we use double and triple integrals to, say, compute surface areas, volumes, masses, centroids. So we use it a lot. We use double and triple integrals quite a bit in physics and also in probability and statistics. So dealing with probabilities of 2 to 3 random variables. So what we're going to be doing in lecture today is we are going to have just a very basic introduction to how to calculate volumes, so the volume under a surface using double integrals. But we're going to approximate those volumes using Riemann sums. And so you probably remember those from single variable calculus, but if not, no worries, because we'll go through a refresher on that. And then we'll also use the Riemann sum definition to introduce the formal definition of double integration. And then next class, we will be evaluating definite double integrals. All right, so let's get started. All right, so just a little definite integral review here, back from single variable calculus. So if f is a function of x, is defined on the interval where a is less than or equal to b, where a is less than or equal to x is less than or equal to b, we're going to divide the interval from a to b. So these square brackets just mean including a and including b, so that's just another way to write that, into n subintervals, where we have x sub I minus 1 to x sub I of equal width. Delta x is equal to b minus a over n. And then we're going to select sample points, some x sub I star from the subintervals. All right, so our subintervals are going to be the width of one of these bars. So this here would be an example of a delta x. And we defined these brackets that we're going from x sub I minus 1 to x sub I. So our first one is going to be x sub 0 to x sub 1. Then we have the interval x sub 1 to x sub 2, x sub 2 to x sub 3, and x sub 3 to x sub 4. And the width of each one of these intervals is going to be defined as going from the full length here, so a to b, and divide by our number of intervals. So in this case, n is equal to 4. So the width 1 delta x is going to be equal to b minus a over 4. Now, of course, we are showing y versus x on this graph here, and our function is this curve. And what we're doing here is we're trying to approximate the area under the curve, which formally, when we evaluate a single integral from a to b, we are computing the exact area under that curve. Now, so this curve represents our function. This is f of x. And so let's just say we were selecting a midpoint to be representative of this entire interval, this delta x here. And so this sample point would be x sub 3 star. Okay, and that's a star. Here would be x sub 1 star, x sub 2 star, x sub 3 star, and x sub 4 star. And what we're doing when we try to determine what the area under this curve is that we're plugging x sub 3 star into our function, and that output is going to be representative of this entire bar. So actually, let me just rewrite this elsewhere so it looks a little more obvious. So I'll do it in a different color too. And so this height right here is going to be representative of this whole interval. So you see that some of the bar is above it, some is below it. And so our output is going to be the function evaluated at x sub 3 star. Okay, so that's a little intro to the syntax here. So what we're doing is we're taking the sum from I equals 1 to n, and then what we're doing is we're going to plug in x sub I star into our function times delta x, okay, from 1 to 4. And so x sub 1, f of x sub 1 plus f of x sub 2 plus f of x sub 3 plus f of x sub 4, right? And each one is going to be multiplied by our interval width, which is delta x. And so if we were going to write this as a definite integral, it'd be our integral. So notice this sum right here is summing up discrete values, right? The output of this function times a discrete interval. So when you integrate, this symbol for integration is elongated s. It's also a sum, but you are summing over a continuous function, okay, with continuous variables, whereas with this other sum right here, you're dealing with discrete variables. So we're going from along the interval from a to b, and then we have f of x, so our function, times dx. So remember dx, that d just means this infinitesimal distance, right? And so when we integrate over some function times dx, right, it's summing up the area underneath the entire curve. So formally, this is going to be the limit as n approaches infinity of our sum from I equals 1 to n of f of x sub I star delta x, because as n approaches infinity, our delta x gets infinitesimally tiny. All right, and so that is our formal definition of integration in single variable calculus, right? And so where this is going to be equal to, this is going to give us the area under the curve. So now let's move forward to looking at double integrals. So with double integrals, what we're doing is we're computing a volume under the curve. So we're going to consider some function of x and y, so a multivariable function defined on a closed rectangle. And so down here, you can see that we have, we're in 3 space, and our region, so this region right here is an area, R. So R is going to be defined as going from on the interval from A to B. Okay, so along the X, we're going from A to B, and we're going to multiply that by our interval along the Y, which is from C to D. Okay, and so that's going to be equal to, do brackets, we have x and y, which are elements of r squared, so the reals squared, such that, so this bar means such that a is less than or equal to x is less than or equal to b. So that's our interval along the x. And c, I can't fit it next to a is less than or equal to x is less than or equal to b, so I'm just going to put it below. And c is less than or equal to y is less than or equal to d. Okay, so R is our area here. So this is the area projected onto the xy plane below our curve. And sorry, it's not a curve, this is our surface. And our surface is represented by z is equal to f of x and y in this case. And so S we're going to define as the solid above R and under F. Okay, so S is the volume here. Okay, so what we're doing, before what we were doing in single variable calculus is we were approximating an area under a curve. Now with double integration, we're approximating a volume underneath a surface. Okay, and so this light blue shaded region here is going to be our S, our solid. And so S is going to be X, Y, Z, because we're in 3 space, it's a solid, that are elements of R cubed, so the reals cubed, such that 0 is less than or equal to Z is less than or equal to F of X and Y, right? So we're in the positive, we're above the XY plane. And X and Y are elements, or sorry, X and Y are in our shaded region here. That R is not the reals, that is our shaded region. All right, so we're limited to the X and Y's in our shaded region to get the output for this function where we're defining Z. So this is how we're defining S. Okay, so let's now go through the steps of how to find the volume under this surface using Riemann sums. Okay, so what we're going to do is we are going to first divide the rectangle R into sub-rectangles. Okay, and you can sort of see these rectangles above on the curve, so pretend that they're projected below. I will try to draw some. So you're going to divide this region into equivalent, pretend these are equal, well, equivalent at least, whoa, okay, that's bad, but anyway, we're going to divide them into rectangles. So A to B, okay, along the X is going to be divided into M, so in this case I drew 1, 2, 3, 4 subintervals. So similar to single variable calculus of equal width, which is given by delta X is equal to B minus A over M. So right here would be our delta X. Okay, width of 1. And N subintervals along the Y, right, from C to D. And so here we have 1, 2, 3, 4, 5, 6. So we would have N equal to 6 in this case, and this would be representative of a delta Y. Okay. And I could also just draw this in an overhead view, so maybe it's a little easier to see. So y versus x. Let's make a rectangle. So this red is representative of our region R. Okay, and it's going to extend along the y from C to D. And along the x from A to B. So those are its extents. Okay, and so if we look at, say, one subinterval, this would be, say, delta x, and it'll go from x sub I minus 1 to x sub I, and this whole thing would be delta x. For delta y, okay, this would be from y sub j, well, so from y sub j minus 1 to y sub j, and this would be delta y. Okay, and then I just want to zoom in here. So one cell, this one cell would be r sub I sub j if we wanted to identify it. All right. So let's move forward. So then second, we choose a sample point in each r sub I sub j. So looking at each one of these, right, so we're going to have like some r sub 1, 1, r sub 2, 1, r sub 3, 1, r sub 4, 1, right, counting along the x. And if we wanted to count along the y, it would be r sub 1, 1, r sub 1, 2, r sub 1, 3. Right, the i's represent where you are in the x, and the j's represent where you are along the y's. And so you choose a sample point in each r sub ij to approximate the part of S that lies above each sub rij by a thin column with base r sub ij and a height given by that sample, each sample point, a x star sub ij and y star sub ij put into our function. So the volume in the column is going to be f of x sub ij star y sub ij star times delta A. And delta A is, of course, going to be, if you're changing area, it's going to be delta x times delta y. And so the volume is going to be approximately equal to the double sum. So from I equals 1 to m. Okay, remember that's our number of intervals along the x. And from j equals 1 to n of our function evaluated at our sampling point. So you can use a midpoint, you can use a corner, it just depends on what you decide, and you need to be consistent. X sub ij star and y sub ij star times delta A. Okay, and this is called the double Riemann sum here. So this is the double Riemann sum. Okay, and so now let's throw in our formal definition of double integration. So V is going to be equal to the limit of m as m and n, it's supposed to be an n, there we go, approach infinity of the double Riemann sum, I equals 1 to m times j equals 1 to n of f of our sample points times delta A, which is going to be equal to our double integral over our region R of our function times dA. So where you take the sample points, these x stars, y stars, become less and less important the smaller your delta A becomes. So look over to the right, for example, right? So here we just have one interval, m equals 1, n equals 1, and so we have our sample point taken at the center. And then you can see that this cube is being used, or box is being used to approximate the volume of a hemisphere, which is not, it's not under a hemisphere, which it's not doing a very good job. So then we add some more intervals and it gets a little better. We add even more intervals, it gets a little better. We add even more intervals and we get a better approximation. But you can see that the more intervals you have, it becomes less important where you take the sampling point. So for example, taking the sample point here at the center of this box is going to give a different value. It's going to give something near the apex of the dome. Whereas if you take your sample at one of the corners, it's going to give you a smaller output for your function, right? Because you're going to be along the surface of the dome here. So it's going to either over or under approximate your volume based on the sample point you take. And so the more sample points you have, the more intervals you have, the less important it becomes where you take your sample point. Okay, now you're definitely ready for an exercise, I promise. So what we're going to do is we are going to estimate the volume of the solid that lies above the square. R is going from 0 to 2 by 0 to 2, and below, one second, sorry, just noticed this. And below, the elliptic paraboloid given by f of x and y is equal to 16 minus x squared minus 2y squared. And we're going to divide our region into, I did a very good job typing this morning, sorry guys, into 4 equal squares. And we're going to choose the sample point to be the upper right corner of each square, r sub I, j. So let's set this up. Okay, so we have y versus x. Okay, and we're going from 0 to 2 for each. So that's at least pretty easy for us to draw. I'm going to set up our region. Okay, so there's our region. So this would represent R sub 1, 1. Here would be R sub 2, 1. Here's R sub 2, 2. And R sub 1, 2. Right, so these are referencing each cell. And so for R sub 1, 1, x is 1, y is 1. For R sub 2, 1, X is 2, Y is 1, and onward. And what we're doing is we want the upper right corner of each square to be our sampling point. So we're going to sample from 1 at 1, 2 for R1, 2. We're going to sample at 2, 2 for R2, 2. We're going to sample at, oh, sorry, that's the wrong corner. Got distracted. We're going to sample at 1, 1. And we're going to sample at 2, 1. So we have our function. Okay, f of x and y is equal to 16 minus x squared minus 2y squared. And the area of each r sub ij equals 1, and m is equal to n is equal to 2. Our number of intervals along the x is 2, and our number of intervals along the y are 2. So our volume can be approximated as the double Riemann sum from I equals 1 to 2 and j equals 1 to 2 of f x I y j times delta a. All right, these are going to be our sampling points for each. So, and we're using the upper right corner. All right, so let's write this out. So our volume is going to be approximated by f of 1, 1 plus, times delta A plus f of 1, 2 times delta A plus f of 2, 1 times delta A plus f of 2, 2 times delta A. And of course, you could have pulled out the delta A, and you end up with, well, delta A is going to be equal to delta x times delta y, and delta x is equal to 1 and delta y is equal to 1, so delta A is equal to 1. And so volume is going to be approximately equal to our delta A, which is 1, times f of 1, 1. And so we need to plug that into our function above. So it's going to be 16 minus 1 minus 2. And so we get 13 plus. So then our f of 1, 2 is going to be 16 minus 1 minus 2 times 2 squared, which is going to give us 7. And then 2, 1 is going to give us 16 minus 4 minus 2, which is 10. And then lastly, we're going to have 16 minus 4 minus 2 times 4, which is going to give us 4. So our volume is 34. Okay. So now let's move on to another. And in this one, what we're gonna do something a little bit different. And the problem is if R is going to be between -1 and 1 for x and -2 and 2 for y, lets us evaluate this surface below. And so we want to figure out what the volume is. And so I'm going to set this up for us. Z is going to be coming out of the page, or going up. And this will be X. And here will be Y. Coming out of the page. Okay, and so we're told X goes from -1 to 1. And so looking at this, this point would be 1, 0, 0, and the -1 is on the other side. Okay, and let's see, Y is going from -2 to 2, and so let's say this is going to be 0, 2, 0, and so that means the radius of the cylinder here is 1, and so up top we have 0, 0, 1 for our Z. And so we need to interpret this, we're trying to interpret this as a volume. And so we have our double integral over region, and our equation's going to be 1 minus x squared dA. So that's going to be our function. And we're going to interpret this as a volume if Z is equal to the square root of 1 minus x squared. Plotting our cylinder here, well, our half cylinder. And then in that case, x squared plus y squared plus, x squared plus z squared is going to be 1, and z is greater than or equal to 0. You can see that all our values are z are greater than or equal to 0, and that x squared plus z squared is going to equal 1. And so we don't have any, we're not below the xy plane at all here, no negative values for z. So this is going to be the volume of a solid S that lies below the circular cylinder x squared plus y squared is equal to 1. Okay, so how are we going to approximate then the volume? So got to do a little bit of critical thinking on this. So, well, what we have here is the area of a half circle. So in order to calculate the area of a half circle, it's going to be pi r squared divided by 2. And then to get the volume, all we do is multiply by the length. So it's how you would expect to determine the volume of a half cylinder. But that's also telling us that when we formally evaluate this integral, that's what we get at. But let's just use the approximation. And so V is going to be equal to the area of a semicircle, so 1/2 pi r squared times our length. So it's going to be equal to 1/2 pi times 1 squared times our length, which goes from -2 to 2, which is 4. So our volume is going to be 2 pi. All right. Now we have one more to go through today. And this is going to be, first we're going to look at the midpoint rule for double integrals. So we have a double integral over some region of our function of x and y dA is going to be approximately equal to the double Riemann sum from I equals 1 to m and j equals 1 to n of x sub I bar y sub j bar times delta A. And in this case, the bar represents our midpoint of our interval. So from x sub I minus 1 to x sub I, or from y sub j minus 1 to x sub j. And so we're going to use the midpoint rule with m equals n equals 2 to estimate the double integral over r of x minus 3y squared dA, where our region is going to be defined in the xy plane such that 0 is less than or equal to x is less than or equal to 2, and 1 is less than or equal to y is less than or equal to 2. Okay, so now let's draw out our region, give it a sketch. And this is going to be from, this is y versus x. One, 2. So we're going from 0 to 2 for x. And we're going from 1 to 2 for y. Okay, so I'm going to draw out our region from 1 to 2 for y, and from 0 to 2 for x. Okay, and I'm just going to set these up. So it's going to be with m equals n equals 2, so we want to split each in half. So we have 4 cells that we're looking at, and we need to get the midpoint of each. Right, where this would be r sub 1, 1. This one's r sub 2, 1. This one's going to be r sub 2, 2. And this one's going to be r sub 1, 2. So we have to find the coordinates of each midpoint here. Okay, so we need x bar sub 1 is going to be, so the midpoint of r sub 1, 1 is going to be 1/2. And then we take the midpoint of x sub bar 2. Okay, and that's going to be 3/2. And then we need the midpoint of y sub 1 bar. Okay, and so that one, so let's see, so between 1 and 2 is 3/2, and so it's going to be in between 1 and 3/2, so this is going to be 5/4. And then y sub 2 bar is going to be 7/4. So that means that delta A is equal to 1/2. And because, okay, so then delta A is equal to 1/2 delta X times delta Y. And now let's compute, let's try to approximate our volume. So V is going to be approximately the sum from I equals 1 to 2 times J equals 1 to 2 of F X sub I bar Y sub J bar times delta A. Okay, so this is going to be equal to delta A times F sub X bar 1, Y bar 1, plus F X bar 1, Y bar 2, plus our function evaluated at X bar sub 2, Y bar sub 1, plus F of X bar sub 2 and Y bar sub 2. All right, so this is going to equal 1/2 times, so then we're just plugging, for example, we're looking at F of 1/2 and 5/4 here, so we're plugging X equals to 1/2 into our function, which is X minus 3Y squared, and we're plugging Y equals to 5/4 in there. And so we have minus 67 over 16 plus, or everything's going to be negative here. So it's going to be minus 67 over 16 plus a minus, which is a minus 139 over 16 minus 51 over 16 minus 123 over 16. And so we get minus 95 over 8. Okay, sorry, it got a little messy there at the end, but that is just about it for today. There's just one more thing I want to show you. Yeah, I'm running out of room. Let's see if I can make a little more room down here. Here we go. All right, so one more thing. I just want to give you one definition, and then we'll be done with this lecture. So our definition of average value for a function is going to be f average. It's going to equal 1 over the area of our region times the double integral over our region of our function dA. Okay, so that gives you the average value because we're dividing by the area. Okay, so it's going to be per area. All right, so that is it for that lecture, and I will see you next time.